Good day, everyone. Welcome to this lecture, Vibration and Noise Control, focusing specifically on principal coordinates and coordinate coupling. We are going to explore how these concepts apply to a simple mechanical systems. This concept is essential for analyzing and controlling vibration in day-to-day problems. My name is Dr. Sindhamari Kannan. I am Associate Professor in the Department of Mechanical Engineering at SVC. Have you ever watched a pendulum swing? Its motion seems simple, but it hides a deeper complexity. This complexity arises from the interplay between different types of motions. This seems imagine a sail swinging on a swing. As they swing back and forth, they also tend to rotate slowly. This twisting motion is coupled with the swinging motion. They influence each other, creating a more intricate movement. Similarly, if you think about a top, spinning top, it spins rapidly around its axis, but it wobbles also. This wobbling is another type of motion coupled with the spinning. Together, they also creating some characteristic dances. In these examples, we see different types of motion intertwined. To understand these types of complex systems and motions, we first have to simplify them. That means we have to separate the motions. This is where the concept of principal coordinates comes in. It's like finding the hidden building blocks of motions. By identifying these fundamental motions, we can break down the complexity and analyze the system more easily. Imagine, with respect to the swinging itself, we would then see two simpler motions, each independent of the other. These independent motions are principal coordinates. One is swinging, another is a small twisting. Sometimes it will happen. Similarly, in spinning also, we are having the wobbling as well as spinning. There also the underlying concept of principal coordinates is there, and that governs the equation of vibrations. By understanding principal coordinates, we can able to gain deeper insights. This knowledge about principal coordinates is very much essential to design bridges also sometimes that can able to withstand vibrations to create musical instruments that to produce beautiful sounds. Principal coordinates help us unravel the complexities of motion and harness its power. Now let's delve deeper. These two figures, they are with respect to a lathe. This figure A and figure B. We are going deeper and analyzing the motion of this lathe. The figure A presents a system where rigid body is suspended by springs. This could represent vehicle suspension, even a building foundation. Here it is a lathe with its legs. The legs here is modeled as springs, a mathematical model. Notice how the springs are attached at a different points on this body. This configuration leads to coupling between translational as well as rotational motions. When the body moves vertically, it also tends to rotate. Similarly, when it rotates, it also experiences a vertical displacements. This interplay between translation and rotation is the hallmark of coordinate coupling. Similarly, let me focus on figure B. It's the same system where the springs are attached in a way that minimizes the coupling. Coupling in sense, the coupling of two motions, linear as well as rotational motions. The symmetrical arrangement of the springs ensures that when the body moves vertically, it experiences minimal rotations and vice versa. The configuration effectively decouples the translation and rotational motions. It's like achieving a state of harmony where each motion can exist independently without influencing the other. Comparing these two figures, we can see how the arrangements of springs can significantly impact the degree of coordinate coupling. In figure A, the coupling is pronounced, while in figure B, it is minimized. Understanding this kind of configurations is very much crucial in designing the systems so that we can effectively control vibration and noise. Here we have a system consisting of mass m with moment of inertia J naught. It is connected to two springs K1, K2 at point A and B respectively. The distance between the center of gravity to these points are L1 and L2. Be interested in this system's motions. We define x of t as the linear displacement of the center of gravity and theta t is the angular displacement. Now let's look at the displacement of the springs. The displacement of the first spring x1 is related to the linear and angular displacement by its equations. That is x1 equal to x minus L on theta. Similarly, the displacement of the second spring is x2 equal to x plus L2 theta. Since this is taken as negative displacement, this one is taken as the positive displacement. Here it is positive, here it is negative. The forces exerted by the springs are proportional to the displacements. So the force from the spring K1 is K1x1. We can rewrite as K1 x minus L1 theta. Similarly, the force from K2 can be rewrite as K2 into x plus L2 theta. The system demonstrates the coordinate coupling, that is, the linear displacement and angular displacement theta are coupled because the spring forces depend on both of them. This coupling makes the analysis more complex. We need to find a way to decouple these coordinates. That's where the principal coordinates comes in. By transforming our coordinates, we can find a new set of coordinates where the equation of motion are uncoupled. This simplifies the analysis and allows us to understand the system's behavior more easily. Once again, we just look into the displacements. That is, the displacement of the first spring is x minus L1 theta. This shows how both linear and rotational displacements contribute to the spring deformation. Similarly, the displacement of the second spring also have both linear and rotational deformations. Once again, I emphasize the forces. Forces exerted by the springs are proportional to the displacements. Therefore, the force from spring K1 is K1 x minus L1 theta and force from spring K2 is K2 x plus L2 theta. These forces will cause the beam to move and rotate. Now we move on to the next one, that is in this diagram. Here we introduce a point P which is away from the center of gravity where we are measuring the vertical displacement y of t at this point. The distance from point P to the spring attachment are L1 and L2. The displacement of the spring are now, here it is changed, that is y minus L1 theta and y plus L2 theta. This expression shows how the vertical displacement at point P and the rotational displacement contribute to the spring deformations. The force exerted by the springs, therefore, it is stiffness multiplied with the displacement term. So here it is stiffness K into Y minus P1 theta. These forces will cause the beam of this lathe move vertically at point P and also to rotate. The key difference between diagram A and B is the point at which we are measuring the vertical displacement. In diagram A, we are measuring it at the center of gravity, while in diagram B, we are measuring it at the point P. This choice affects the way we describe system motions and resulting equations. In essence, the principal coordinates allows us to treat the system, and if it were made up of independent oscillators, by finding these coordinates, we can determine the natural frequencies and mode shapes of the systems, which are very much crucial for vibration analysis. From the previous slide, we continue our discussion. Here, we have a system connected of a mass m with a moment of inertia of J naught. It's connected to two springs K1 and K2 at point A and B respectively. The distances from the center of gravity to these points are L1, L2. We are interested in the system's motions. We define x of t as the linear displacement, theta of t is angular displacement. Now let's look at the displacements of the springs. The displacement of the first spring x1 is related to the linear as well as angular displacement by this equation we already discussed in the previous slide. Similarly, the displacement of the second spring is represented by this equation. The forces exerted also we discussed in the last slide just now. That is, the force from the spring is K1x1. The force from the spring 2 is K2x2, where we are substituting the x2 value and xn values. Now, this system exactly demonstrates the coordinate coupling, that is, linear displacement x and angular displacement. You can see in this a single equation we are having both the terms x as well as theta. That means this linear displacement and angular displacement are coupled because the spring force depends on both of them. This coupling makes the analysis more complex. Hence, we have to go for principal coordinates. By transforming these coordinates, we can find a new set of coordinates where the equation of motions are totally uncoupled. That means x equations are separated, displacement in terms of linear is separated, and rotational displacements are separated. In essence, once again, I am emphasizing that principal coordinates allows us to treat the system. By finding these coordinates, we can determine the natural frequencies. Here, we are having a lathe. We are going to discuss about this machine that rotates the workpiece. In simplified model, we are examining how the lathe motion is affected by its support structure, specifically with respect to the springs. We are looking at what happens when lathe experiences both vertically and rotational movement. Here we have a diagram representing our lathe system where we are representing mathematically the masses as mass m, moment of inertia as J naught. It is supported by two springs K1 and K2 located at a distance L1 and L2 from point P, that is center of gravity of the lathe. We are interested in understanding the vertical displacement y of t and rotational displacement. As the text here, we are having the equation. This crucially, the motions are going to be whether we are coupling it or uncoupling it. It is to be seen how to couple and uncouple the equations. If it is to be coupling to be disabled, then we have to go for K1 L1 equal to K2 L2. This, if it is satisfied, then it is going to be known as elastic or static coupling. Look at the displacement of the springs. The first spring displacement is y minus L1 theta. Second spring is y plus L2 theta. This expression shows how both vertical and rotational displacements contribute to this spring deformation. The first equation describes the vertical motion, that is mass into acceleration. This is y double dot. This acceleration equal to minus k1 y minus L1 theta minus k2 y plus L2 theta minus mc theta is a term related to the coupling effect. The second equation describes the rotational motion. Here, J theta is the initial torque, K terms as the spring torques, and M, the last term, is with respect to the coupling term. These equations are derived from Newton's second law, and also we can use it for both linear as well as rotational motion. Remember, the key understanding the system like this coordinate coupling is where K1 L1 equal to K2 L2. When this condition met, coupling terms disappear, then that we call it as static coupling. In essence, this system demonstrates how the placement and stiffness of springs can influence the motion of a rigid body. By understanding the equation of motions and concept of elastic coupling, we can design the systems that can more effectively demonstrate the real-time systems. Here, we see the equations of motions written in matrix form. In previous slide, we written in the form of the equation itself. Here, the first equation, we can able to see that the matrix and the J terms, it will be going to be called as the mass matrix, and the initial term is going to be there, that is, it is going to with respect to linear and rotational motions. The y double dot and theta double dot terms are acceleration and linear rotational only. The next matrix, you can able to see that k1 plus k2, k2 L2 dash minus k1 L1. This you know that using the equation of motion we can able to create that, and afterwards this is now arranged in the form of matrix. Now that we can able to see that a very important condition, that is K1 L1 equal to K2 L2, the system will have dynamic or inertia coupling only when this is going to be followed. This means that even if the spring force balances out in certain way, the system still has coupled motions because of its inertia. That is, we can able to tell once again the same example, that imagine a spinning object that also moves up and down. Even if the springs are perfectly balanced, the spinning can still affect the up and down motion. At last, this equation is the more general form, showing a viscously damped 2-degree of freedom system where this term represents mass matrix, this term represents damping matrix, and this term is the stiffness matrix, where x double dot is acceleration, x dot is velocity, simply x is displacement vector. This equation includes damping as well as, which is the dissipation of energy like friction. Notice how these matrices are all 2 by 2. This is because we are looking at systems with 2-degree of freedom systems, in our case linear and rotational motions. The off-diagonal terms in these matrices are crucial. They show how different motions are coupled. If these terms are zero, the motions will become independent. In summary, this matrix equations provides concise and powerful way to describe the motion of complex systems. This allows us to analyze the effect of mass, stiffness, and damping in real-time applications. We already seen that principal coordinate concept and the coordinate coupling concept. Now we are going to conclude this concept with some very important points. Those things is going to be that these principal coordinates are special coordinates that simplify the equations. They are like finding the right language to describe the system's motions. Principal coordinates give us equations that are uncoupled. This means that each coordinate represents an independent mode of vibration. We can analyze each mode separately, making the whole system much easier to understand. So remember, the system will vibrate in its own natural way, regardless of the coordinates we use. But choosing the right coordinates, especially principal coordinates, can make our analysis much simpler. It's like finding the right tool for the object. We use coordinates for convenience, but principal coordinates reveal the true uncoupled nature of systems vibrations. We have talked about how complex systems can have coupled motions. Now, let's look at a specific example, a spring mass system. Here, we have two masses connected by springs, and we want to find principal coordinates that simplify this analysis. Let's see how the arrangement is. The mass m1 and m2 are going to be have the same equal mass. Let me denote it as m1 equal to m, m2 equal to also m. They are connected by three springs. The top spring K1 has a stiffness K, the middle spring K2 has a stiffness. It is in terms of why we putting nk means it may be taken as nth factor. That is, it is a factor. And the bottom spring K3 also has a stiffness K. Displacement of the masses are represented in terms of x, that is, mass m1 is represented as x1 times of t, and mass m2 represented in terms of x2 with respect to t. We want to find a new set of coordinates, the principal coordinates, that will allow us to analyze the system vibrations more easily. Remember, principal coordinates are special. They can able to decouple the equations of motion. This means we can treat each coordinate as an independent oscillator, making the analysis much simpler. In this system, the motion of the two masses are coupled. When one mass moves, it affects the other. By finding the principal coordinates, we will be able to see the system's natural modes of vibrations independently. To find these coordinates, we will need to set up equation of motions, find the mass, stiffness matrix, and solve for eigenvalues and eigenvectors. What is eigenvalues and eigenvectors? These eigenvectors will give us the principal coordinates. Eigenvalues will give us the natural frequencies of the system. So let's get started to find principal coordinates for this spring mass system. We have set up our spring mass system, and now it's time to find the principal coordinates. Remember, these coordinates will help us very greatly to understand the system's vibrational behavior in a simpler way. The first step is to define two independent solutions as a principal coordinates and express them in terms of solutions x1 of t and x2 of t. This means we are looking for very two new coordinates that can able to represent the system motion without any coupling terms. Now let's look at the general motion of the system. We see that the displacements x1 of t and x2 of t are described as a combination of cosine terms. This cosine term represent system natural modes of vibration. Notice the terms inside the cosine functions, that is root of k by m and 3k by m. These are the natural frequencies of the system itself. They tell us how fast the system oscillates in each of its modes. The constants B1, B2 represent the amplitude of the vibration in each mode, and pi1, pi2 are the phase angles. which tell us the initial position of the system at time t equal to 0. Observe how this x1 of 2 and x2 of 2 are related. They both contain the same cosine terms but with different signs. This relationship is crucial for understanding the system's behavior. These equations show that motion of the system can be expressed as a combination of two independent solutions. These independent solutions are the principal coordinates what we are looking for. They represent the system's natural mode of vibration decoupled from the other mode. In essence, the equation 1 represents system's general motion in terms of its principal coordinates. By expressing the motion in this way, we can analyze each mode of vibration separately, making the system much easier to understand. We have been working on finding the principal coordinates of the given spring mass system. Now let's see what to do. We start by defining the new set of coordinates, that is q1 of t and q2 of t. These are set of new principal coordinates. They are chosen in such a way that they represent the independent modes of vibration of our system. Notice that q1 of t and q2 of t are both cosine function. This tells us that the motions they represent are harmonic. They can able to oscillate back and forth smoothly. Q1 of t has a frequency of root k by m and Q2 of t has a frequency of 3 k by m, that is the square root of it. These are the natural frequencies of our systems. These q coordinates are special. They are chosen so that each one represents single independent modes of vibration. This means we look at q1 of t, we are only seeing one specific way the system can vibrate, and we look at q2 of t, we are seeing a different completely independent way the system can vibrate. This is going to be telling us that the coordinates are harmonic functions. The corresponding equations can be written in terms of very simple two equations. Let's look at that equations, that is q1 double dot, that is acceleration plus k by m into q1 equal to 0. Similarly, the second equation of motion represents q2 double dot, where it once again represents the acceleration. Notice how these equations only involves q1 and its derivatives. There is no q2 term in the first this equation. Similarly, in the q2 equation, there is no q1 term. This means that the motion described by q1t is completely independent by q2 of t. Similarly, the second equation q2 plus 3k by m is 0. No, this equation of motion is going to be the main important thing. We have to see that this shows that the motion described by q2 of t is also independent of q1 of t. These simple equations are all the hallmark of the principal coordinates. They show that the motions can be broken down into independent harmonic oscillations. This makes the analysis much simpler because we can study each mode of vibration separately. So once again, it is very impressive that principal coordinates, we have transformed a complex coupled system into two simple independent oscillators. This is the power of principal coordinates. That is, they are simplifying the complex systems by decoupling them. We defined our principal coordinates q1 of t and q2 of t and seen their independent equations of motions. Now let's see how they relate to the original coordinates x1 of t and x2 of t. The first set of equations shows it is going to be that original coordinate x1 of t, x2 of t can be expressed in terms of new principal coordinates, that is q1 of t and q2 of t. We see that once again, see the equation, that is x1 of t is simply the sum of q1 of t and q2 of t, while x2 of 2 is the difference between, it is not sum, it is difference. See the difference once again. This difference. The difference between Q1 of t and Q2 of t. These equations tells us that the original motions of masses x1 of t and x2 of t are actually combination of the two independent modes of vibration represented by these terms q1 of t and q2 of t. In other words, the coupled motion we observed in x1 of t are just the result of combining the uncoupled motions q1 of t and q2 of t. Let's see the second set of equations. These equations show how we can find the principal coordinates from the original coordinate system, that is x variable. The q1 of t is equal to 1 half of the sum of x1 of t and x2 of t, while q2 of t is equal to 1 half of the difference between x1 of t and x3 of t. These equations are key to unlocking the principal coordinates. They allow us to transform our original uncoupled coordinate into a new set of coordinate system that represents independent modes of vibration. This transformation simplifies the analysis of the system because we can now study each mode separately. Now, concluding this, that is, we are providing a bridge between original coordinates and principal coordinates. This shows us how to express the system motion in terms of its independent modes of vibration, making the analysis much simpler and more insightful. Today, in this video, we have discussed major important concept, that is principal coordinate and coordinate coupling. Thank you. See you in the next session.